Generation IV reactors are a set of nuclear reactor designs currently being researched for commercial applications, with, depending on the particular design, technology readiness levels varying between the level requiring a demonstration to economical competitive implementation. Most of these designs, with the exception of the BN1200 reactor, are generally not expected to be available for commercial construction before 2030 to 40. Presently, the majority of reactors in operation around the world are considered second-generation reactor systems, as the vast majority of the first-generation systems were retired some time ago, and there are only a dozen or so Generation 3 reactors in operation. Generation V reactors refer to reactors that are purely theoretical, and are therefore not yet considered feasible in the short term, resulting in limited R&D funding. Reactor types. Many reactor types were considered initially, however, the list was downsized to focus on the most promising technologies and those that could most likely meet the goals of the Gen IV initiative. 3 systems are nominally thermal reactors and 3 are fast reactors. The very high-temperature reactor is also being researched for potentially providing high-quality process heat for hydrogen production. The fast reactors offer the possibility of burning actinides to further reduce waste and of being able to breed more fuel than they consume. These systems offer significant advances in sustainability, safety and reliability, economics, proliferation resistance and physical protection. Thermal reactors. A thermal reactor is a nuclear reactor that uses slow or thermal neutrons. A neutron moderator is used to slow the neutrons emitted by fission to make them more likely to be captured by the fuel. Very high temperature reactor. The very high temperature reactor concept uses a graphite-moderated core with a once-through uranium fuel cycle, using helium or molten salt as the coolant. This reactor design envisions an outlet temperature of 1000 degrees Celsius. The reactor core can be either a prismatic block or a pebble bed reactor design. The high temperatures enable applications such as process heat or hydrogen production via the thermochemical iodine-sulfur process. It would also be passively safe. The planned construction of the first VHTR, the South African PBMR, lost government funding in February 2010. A pronounced increase of costs and concerns about possible unexpected technical problems had discouraged potential investors and customers. The People's Republic of China began construction of a 200 MW high-temperature pebble bed reactor in 2012 as a successor to its HTR-10. Also in 2012, as part of the next-generation nuclear plant competition, Idaho National Laboratory approved a design similar to Arava's prismatic block Antares reactor as the chosen HTGR to be deployed as a prototype by 2021. It was in competition with General Atomic's gas turbine modular, helium reactor and Westinghouse's pebble bed modular reactor. Molten salt reactor. A molten salt reactor is a type of nuclear reactor where the primary coolant, or even the fuel itself, is a molten salt mixture. There have been many designs put forward for this type of reactor and a few prototypes built. The early concepts and many current ones rely on nuclear fuel dissolved in the molten fluoride salt as uranium tetrafluoride or thorium tetrafluoride. The fluid would reach criticality by flowing into a graphite core, which would also serve as the moderator. Many current concepts rely on fuel that is dispersed in a graphite matrix with the molten salt providing low pressure, high temperature cooling. The Gen IV MSR is more accurately termed an epithermal reactor than a thermal reactor due to the average speed of the neutrons that would cause the fission events within its fuel being faster than thermal neutrons. The principle of a MSR can be used for thermal, epithermal and fast reactors. Since 2005, the focus has moved towards a fast-spectrum MSR. Supercritical water-cooled reactor. The supercritical water reactor is a reduced moderation water reactor concept that, due to the average speed of the neutrons that would cause the fission events within the fuel being faster than thermal neutrons, it is more accurately termed an epithermal reactor than a thermal reactor. It uses supercritical water as the working fluid. SCWRs are basically light water reactors operating at higher pressure and temperatures with a direct, once-through heat exchange cycle. As most commonly envisioned, it would operate on a direct cycle, much like a boiling water reactor. But since it uses supercritical water as the working fluid, it would have only one water phase present, which makes the supercritical heat exchange method more similar to a pressurized water reactor. It could operate at much higher temperatures than both current PWRs and BWRs. Supercritical water-cooled reactors are promising advanced nuclear systems because of their high thermal efficiency and considerable plant simplification. The main mission of the SCWR is generation of low-cost electricity. It is built upon two proven technologies, LWRs, which are the most commonly deployed power-generating reactors in the world, and superheated fossil fuel-fired boilers, a large number of which are also in use around the world. The SCWR concept is being investigated by 32 organizations in 13 countries. SCWR design under development is the VVER 1700 and 393, a Russian supercritical water-cooled reactor with double inlet core and a breeding ratio of 0.95. Fast reactors. A fast reactor directly uses the fast neutrons emitted by fission, without moderation. Unlike thermal neutron reactors, fast neutron reactors can be configured to burn, or fission, all actinides, and given enough time, therefore drastically reduce the actinides fraction in spent nuclear fuel produced by the present world fleet of thermal neutron, light water reactors, thus closing the nuclear fuel cycle. Alternatively, if configured differently, they can also breed more actinide fuel than they consume. Gas-cooled fast reactor. The gas-cooled fast reactor system features a fast neutron spectrum and closed fuel cycle for efficient conversion of fertile uranium and management of actinides. The reactor is helium-cooled and with an outlet temperature of 850 degrees Celsius. It is an evolution of the very high-temperature reactor to a more sustainable fuel cycle. It will use a direct Brayton cycle gas turbine for high thermal efficiency. Several fuel forms are being considered for their potential to operate at very high temperatures and to ensure an excellent retention of fission products. Composite ceramic fuel, advanced fuel particles, or ceramic-clad elements of actinide compounds. Core configurations are being considered based on pin or plate-based fuel assemblies or prismatic blocks. The European Sustainable Nuclear Industrial Initiative is funding 3-generation IV reactor systems, one of which is a gas-cooled fast reactor, called Allegro, 100 megawatts, which will be built in a Central or Eastern European country with construction expected to begin in 2018. The Central European Visegrad Group are committed to pursuing the technology. In 2013, German, British, and French institutes finished a 3-year collaboration study on the follow-on industrial-scale design, known as Go Fast. They were funded by the EU's 7th FWP framework program, with the goal of making a sustainable VHTR sodium-cooled fast reactor. The SFR is a project that builds on two closely related existing projects: the liquid metal fast breeder reactor and the integral fast reactor. The goals are to increase the efficiency of uranium usage by breeding plutonium and eliminating the need for transuranic isotopes ever to leave the site. The reactor design uses an unmoderated core running on fast neutrons, designed to allow any transuranic isotope to be consumed. In addition to the benefits of removing the long half-life transuranics from the waste cycle, the SFR fuel expands when the reactor overheats. and the chain reaction automatically slows down. In this manner, it is passively safe. The SFR reactor concept is cooled by liquid sodium and fueled by a metallic alloy of uranium and plutonium or spent nuclear fuel, the nuclear waste of light water reactors. The SFR fuel is contained in steel cladding with liquid sodium filling in the space between the clad elements which make up the fuel assembly. One of the design challenges of an SFR is the risks of handling sodium, which reacts explosively if it comes into contact with water. However, the use of liquid metal instead of water as coolant allows the system to work at atmospheric pressure, reducing the risk of leakage. The European Sustainable Nuclear Industrial Initiative is funding 3-generation IV reactor systems, one of which is a sodium-cooled fast reactor called Enoshd, Advanced Sodium Technical Reactor for Industrial Demonstration. Areva, CEA and EDF are leading the design with British collaboration. Enoshd will be rated about 600 MWE and is proposed to be built in France, near to the PHE Acute NIX reactor. A final decision in construction is to be made in 2019. The PRC's first commercial-scale, 800 MWE, fast neutron reactor, to be situated near Sanming in Fujian Province, will be ASFR. In 2009, an agreement was signed that would entail the Russian BN-800 reactor design to be sold to the PRC once it is completed. This would be the first time commercial-scale fast neutron reactors have ever been exported. The BN-800 reactor became operational in 2014. In India, the prototype fast breeder reactor, a 500 MWE sodium-cooled fast reactor, is being built at a cost of 5,677 Indian rupees crores and is expected to be commissioned by September 2016. The PFBR will be followed by 6 more commercial fast breeder reactors of 500 MWE each. The 400 MWE fast flux test facility operated successfully for 10 years at a Hanford site in Washington state. The 20 MWE BR2 operated successfully for over 30 years at the Idaho National Laboratory, until it was shut down in 1994. Lead-cooled fast reactor. The lead-cooled fast reactor features a fast neutron spectrum lead or lead bismuth eutectic liquid metal-cooled reactor, with a closed fuel cycle. Options include a range of plant ratings, including a battery of 50 to 150 megawatts of electricity that features a very long refueling interval, a modular system rated at 300 to 400 megawatts, and a large monolithic plant option at 1,200 megawatts. The fuel is metal or nitride-based, containing fertile uranium and transuranics. The LFR is cooled by natural convection with a reactor outlet coolant temperature of 550 degrees Celsius, possibly ranging up to 800 degrees Celsius with advanced materials. The higher temperature enables the production of hydrogen by thermochemical processes. The European Sustainable Nuclear Industrial Initiative is funding 3-generation IV reactor systems, one of which is a lead-cooled fast reactor that is also an accelerator-driven subcritical reactor, called MYRRHA, 100 megawatts, which will be built in Belgium with construction expected to begin after 2014, and the industrial-scale version, known as Alfred, slated to be constructed sometime after 2017. A reduced-power model of MER called Guinevere was started up at MOL in March 2009. In 2012, the research team reported that Guinevere was operational. 2 other lead-cooled fast reactors under development are the SVBR-100, a modular 100 MWE lead bismuth-cooled fast neutron reactor concept designed by OKB Gidropress in Russia, and the Brest-OD-300 300 MWE, to be developed after the SVBR-100, and built over 2016 to 20. It will dispense with the fertile blanket around the core and will supersede the sodium-cooled BN-600 reactor design, to purportedly give enhanced proliferation resistance. Advantages and disadvantages. Relative to current nuclear power plant technology, the claimed benefits for fourth-generation reactors include nuclear waste that remains radioactive for a few centuries instead of millennia, 100 to 300 times more energy yield from the same amount of nuclear fuel, broader range of fuels, and even unencapsulated raw fuels. In some reactors, the ability to consume existing nuclear waste in the production of electricity, that is, a closed nuclear fuel cycle. This strengthens the argument to deem nuclear power as renewable energy. Improved operating safety features, such as avoidance of pressurized operation, automatic passive reactor shutdown, avoidance of water cooling and the associated risks of loss of water and hydrogen generation, explosion and contamination of coolant water. Nuclear reactors do not emit CO2 during operation, although like all low-carbon power sources, the mining and construction phase can result in CO2 emissions, if energy sources which are not carbon neutral, or CO2-emitting cements are used during the construction process. A 2012 Yale University review published in the Journal of Industrial Ecology analyzing CO2 life cycle assessment emissions from nuclear power, determined that the collective LCA literature indicates that life cycle GHG, greenhouse gas, emissions from nuclear power are only a fraction of traditional fossil sources and comparable to renewable technologies, although the paper primarily dealt with data from Generation 2 reactors, and did not analyze the CO2 emissions by 2050 of the presently under construction Generation 3 reactors. It did summarize the life cycle assessment findings of in-development reactor technologies. FBR's fast breeder reactors have been evaluated in the LCA literature. The limited literature that evaluates this potential future technology reports median life cycle GHG emissions similar to or lower than LWR's Gen 2 light water reactors, and purports to consume little or no uranium ore. A specific risk of the sodium-cooled fast reactor is related to using metallic sodium as a coolant. In case of a breach, sodium explosively reacts with water. Fixing breaches may also prove dangerous, as the cheapest noble gas argon is also used to prevent sodium oxidation. Argon, like helium, can displace oxygen in the air and can pose hypoxia concerns, so workers may be exposed to this additional risk. This is a pertinent problem as can be testified by the events of the loop-type prototype fast breeder reactor Monju at Suruga, Japan. Using lead or molten salts mitigates this problem by making the coolant less reactive and allowing a high freezing temperature and low pressure in case of a leak. Disadvantages of lead compared to sodium are much higher viscosity, much higher density, lower heat capacity, and more radioactive neutron activation products. In many cases, there is already a large amount of experience built up with numerous proof-of-concept Gen IV designs. For example, the reactors at Fort St. Vrain Generating Station and HTR-10 are similar to the proposed Gen IV VHTR designs, and the pool-type EBR-2, PHEQ-10IX and BN600 reactor are similar to the proposed pool-type Gen IV sodium-cooled fast reactors being designed. Generation IV International Forum. There are currently 10 active members of the Generation IV International Forum. Canada, China, the European Atomic Energy Community, France, Japan, Russia, South Africa, South Korea, Switzerland, and the United States. The non-active members are Argentina, Brazil, and the United Kingdom. The Generation IV International Forum was founded in 2001. Switzerland joined in 2002, Euratom in 2003, and China and Russia in 2006. The remaining countries were founding members. The 36th GIF meeting in Brussels was held in November 2013. The Technology Roadmap Update for Generation IV Nuclear Energy Systems was published in January 2014, which details R&D objectives for the next decade. A breakdown of the reactor designs being researched by each forum member has been made available.